back to the topic on the acidic character of phenol. Phenol is acidic, more acidic than the alcohols. That is, when we compare the acidic character of phenol, phenols are more acidic than the alcohols. This can be explained by considering various concepts like resonance, etc. Suppose you consider this phenol. Phenol, when it loses a proton, it gives rise to O minus plus H plus. Instead of writing a circle, I will write 3 double bonds. One of the contributing resonance structure for the benzene ring. So this is called phenoxide ion. Phenoxide ion. Suppose you consider an alcohol like methyl alcohol. This methyl alcohol also assume that it ionizes to give rise to CH3O minus and H plus. This is called methoxide ion. When we compare this phenolic group as well as an alkyl group, alkyl group is a positive inductive group. Suppose you write this carbon oxygen bond. This is having positive inductive effect. That's why the negative charge on the oxygen atom will increase. That's why the tendency to accept the proton will be more. That's why instead of methoxide ion and hydrogen ion, it will be a reverse reaction that is easily taking place. That's why the loss of proton from the methanol or any alcohol is less possible because of the less stability of the alkoxide ion. But when you compare with the phenoxide ion will undergo resonance. If you write this resonance structure, this is negative charge because of the loss of the proton from the phenol group. When we consider this, it will undergo resonance like this. The resonance is indicated with the curved arrow. It indicates the migration of the electron density to that particular position. Here from oxygen to this carbon oxygen bond, and double bond is shifted to this. So we get the negative charge on this carbon atom. Here we get double bond. Similarly, this can undergo resonance to give rise to one more structure, that is in the para position. Double bond. This will undergo further resonance to give rise to one more structure, that is with negative charge in the ortho position. Double bond. Because of these 3 important resonance structures, the negative charge from the oxygen is withdrawn. That's why the stability of the phenoxide ion will be increased. Because of the increase in the stability of the phenoxide ion, that is because of resonance structures, stability of phenoxide ion increases. Phenoxide ion increases. Therefore, phenol is more acidic. Phenol is more acidic than alcohols, as alkoxide ions are less stable. Alkoxide ions are less stable. Because of that explanation, because of the positive inductive effect, methyl group or alkyl group pushes the electron density towards the oxygen, increasing the charge on the oxygen atom more. That's why it becomes less possible to undergo ionization, rather it can easily accept the proton. But in this case, because of the decrease in the negative charge on the oxygen atom, it will be more stabilized. That's why the tendency to undergo ionization is more as compared to that of the alcohols. Now let us see the effect of substituents. Effect of substituents on acidic strength. on acidic strength of phenols. First, let us consider electron withdrawing group. For example, when you consider this nitro group, cyano group, halogen atom, aldehyde, etc. These are all electron withdrawing groups. So such compounds will withdraw the electron density from this benzene ring. Whenever they are present in the para position as well as in the ortho position, because of the negative charge in the ortho and para position, that electron density will be withdrawn by these substances. That's why in ortho and para positions, these groups will increase acid strength more than in meta position. For example, if I write these three compounds, nitrophenols, assume that nitro group is present in the ortho position, nitro group is present in the para position or meta position. By some method, if you prepare these three, then to compare these acidic strengths, we will consider this one. In this case, the hydrogen atom of the OH group and oxygen atom of the nitro group, they undergo intramolecular hydrogen bonding. That is this hydrogen. If I write this oxygen like this, then there will be intramolecular hydrogen bonding. That's why this is less acidic as compared to para. But still it is increasing the acidic strength because it takes up the electron density from the ortho position. That's why we can write this as ortho, meta and para. The actual acidic strength is para nitrophenol more acidic than ortho nitrophenol, more acidic than meta nitrophenol. NP stands for nitrophenol. Okay. Suppose similar groups are more in number. As number of groups increase, acidic strength also increases. For example, if I write this 2,4,6 trinitrophenol, 2,4,6 trinitrophenol. This already I told you, this is called picric acid. This will be more acidic as compared to dinitrophenol, 2,4-dinitrophenol. This is more acidic as compared to nitrophenol, OH, NO2, either in the ortho or in the para or in the meta. And this will be in turn more acidic than simply phenol. Okay. So, any electron withdrawing group, especially in the ortho and para positions, there will be more acidic strength for such compounds as compared to meta position. But still, in the meta position, it has a tendency to withdraw the electron density from the benzene ring. That's why the ortho, meta as well as para substituted electron withdrawing groups, substituted by the electron withdrawing groups. They will be more acidic as compared to the unsubstituted phenol. Exactly reverse explanation when we consider the electron donating groups. Okay. So let us consider this second one, electron donating groups. Electron donating groups. These may be either alkyl groups, alkoxy groups, or NO, amino group, etc. Even though the nitrogen is more electronegative than the carbon, because of the lone pair of electron on the nitrogen atom, they can donate. So, such groups will actually decrease the acidic strength. Electron donating groups decrease the acid strength of phenol. For example, alkyl, alkoxy group, NH2 group, etc. For example, especially the explanation is exactly reverse as compared to that of the electron withdrawing groups. Suppose you consider these cresols. There are three isomeric compounds for these cresols, that is metacresol, orthocresol, OH and CS3. Metacresol, OH and CS3 in the meta position, and paracresol, OH and CS3. So this is ortho, this is meta, this is para. Now the exact explanation will be reverse one, because meta group will be having more electron donating effect as compared to that of the ortho and para. That's why this metacresol is more, electron donating effect of the para and ortho will be more as compared to meta. That's why the donating capacity of the ortho in the meta position will be very, very less. That's why metacresol is more acidic. This will be more acidic as compared to paracresol. This will be more acidic as compared to the orthocresol. So this is about the explanation for the acidic strength, change in the acidic strength by the electron donating groups. So CS3 is an alkyl group. Similarly, we can consider this OH group in the OH and OCS3 group. This is called methoxy group. This will again have meta effect more as compared to para as compared to ortho. Suppose both the groups are present, electron donating as well as electron withdrawing group. Depending on their positions, the acidic strength can be decided. That we will consider when we discuss some questions. So that is all about the topic on the phenols. Thank you.